Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the discussion of thermodynamics of open systems as applied to phase equilibrium. We have already seen that for a pure substance, the phase stability can be derived at a given temperature and pressure either by plotting chemical potential as a function of temperature at a given pressure, or we can look at the pressure dependence of phase stability by looking at, for instance, the melting of solid and comparing the plots of chemical potential at higher pressure and a lower pressure, so that we can figure out if the melting point is increasing or decreasing with pressure, depending on whether the molar volume of the solid is greater than or less than the molar volume of the liquid. We have also seen the variation of mu versus T for the liquid gas phase coexistence, and we find that we can actually estimate the amount by which each of these mu versus T curves will shift at higher pressure, so that there will be a change in the boiling temperature as I go from the liquid to the gas phase, and it would be at a higher pressure that the liquid will boil down. Now we are taking up this problem of effective variation of both temperature and pressure on two coexisting phases of a pure substance in equilibrium. Now let me take a step-by-step approach to define the problem. First of all, we need to understand how to construct a one-component phase diagram of a given substance. A phase diagram in general is prepared by plotting temperature and pressure of the given substance. This is simply because both temperature and pressure can be manipulated in the laboratory very easily. Now, for many different values of the pressure and temperature of your working substance, you make a note of whether your substance is a solid or a liquid or a gas. And therefore, in the example shown here, as you would find that at all these combinations of pressures and temperatures, my system is found to be existing in the gas phase, while at these values I find that my system is existing in a single phase, but this phase is no longer the gas phase but the liquid phase. And when I look at very low pressure and very low temperature, this is where I encounter my working substance to have a single stable phase as the solid phase. Now, when I am constructing the phase diagram, this is not a sufficient information about how the system can undergo a change in phase as I go on changing temperature and pressure. So, for this purpose, I will add some more details into this diagram. And here the details are as follows. For example, let me take this particular line. So what does this line signify? It tells me that along each point on this line, I have the condition of temperature and pressure at which the solid and the liquid phase can coexist at equilibrium. Similarly, if I am pointing out certain values of temperature and pressure, what do they give me? They tell me that at these temperatures and pressures, the liquid and the solid phase and the liquid and the gas phase can coexist in equilibrium. And finally, when I have a combination of these pressure and temperature values. I am talking about the phase equilibrium at these temperatures and pressures between the solid phase and the gas phase. Therefore, if I want to know the process, if I go from this value of pressure and temperature to this value of pressure and temperature, I am basically heating up the substance at constant pressure. So, the process involved would be heating of the solid till here, where there will be a single solid phase of the substance. When the temperature reaches this value, the liquid phase will be in equilibrium with the solid, and then when I heat it further, then there will be now again a single phase which is a liquid phase, and there will be heating of the liquid. Similarly, if I am doing an isobaric heating across this curve, I will encounter heating of the liquid followed by an equilibrium between the gas phase and the liquid phase. Finally, I am talking about heating of the single gas phase. Here, the kind of transition that I will have is known as the sublimation of the solid in the gas phase. So, initially, once again, I am going to have a heating of the solid at constant pressure. Then when it reaches this point, I have an equilibrium between the solid and the gas phase, and eventually when I heat the system further, I am going to have heating of the gas. Now, when I have constructed these curves separating the single phase regions of the phase diagram, then I understand that any point which has in this PT area, PT plane, if it is not a part of any of these curves, then it is understood that any point outside these curves is where the system is stable in a single phase. And depending on the values of P and T of where you are, you can either be stable, the system can either be stable in the solid phase or the liquid phase or the gas phase. Now, let me have a look at a typical phase diagram. And here you need to understand that there are certain properties that I need to take care of when I talk about the when I try to understand what this typical phase diagram means. First of all, I have a phase boundary or coexistence curve. So these are these solid lines that I have been talking about, which separate the single phase regions of the substance, and a point on this curve implies coexistence of two different phases of the substance at a given value of temperature and pressure. Now, if I look at the normal atmospheric pressure, then I find that this is the temperature at which the system is going to have a phase equilibrium between the solid phase and the liquid phase, and therefore this is named as the normal melting point. Similarly, at 1 atmospheric pressure, this is the phase at which, this is the temperature at which one can establish an equilibrium between the liquid and the gas phase. So that is the normal boiling point. Now, if you are at 1 bar pressure, that is where you are going to talk about the standard boiling or the standard melting point. Now, as you see that here, there is something very interesting over here. Now, when I have the sublimation, then I am talking about a temperature like this, and therefore for the given phase diagram, the solid at 1 atmospheric pressure will never undergo any sublimation, and that is because the sublimation curve has gone up to this point A, and it does not exist at 1 atmospheric pressure. Similarly, cooling of the gas at 1 atmospheric pressure, even at a very low temperature, will not give you any deposition of the solid. That is simply because, once again, this sublimation curve or the deposition curve, that is non-existent at 1 atmospheric pressure. Similarly, another thing that we note here from the experimental phase diagram, that the phase coexistence line or curve between the liquid and the gas phase, it terminates at a certain point. This point is known as the critical point, and the corresponding temperature, if I mark it out here, is called the critical temperature, and the corresponding pressure is known as the critical pressure. Therefore, I understand that if I have a liquid at a temperature and pressure somewhere here, and if I want to create a phase which is gas-like by heating it up, I can do so by going from here to here, but I will not encounter an interface, that is a liquid-gas interface, as I do so, and therefore beyond the critical point, the liquid and the gas phase, they are similar and they can be continuously transformed between each other. But the same is not true for the solid and the liquid phases, and here the phase boundary or the coexistence line, it continues indefinitely. There is one more point which is of high interest for a phase diagram like this, and this is this point A. Now at this point, what I have is, I have all the three phases coexisting with each other. And now if I look at this phase diagram, I can recall that there is in the literature of phase equilibrium what is known as the phase rule. And the phase rule says that the number of degrees of freedom with respect to drawing of the phase diagram, that is given by C minus P plus 2. So what is C? C is the number of components present in the system. What is P? The number of phases present in the system. And F is the number of parameters that can be varied independently to describe the equilibrium state of the system. Now let us have a very nice simplification. For a pure substance, how many components do you have? You have only one component, and therefore the phase rule can now be read as F is equal to 3 minus P, where P is the number of phases that exist for this pure substance under a given condition. Now let us have a look at what is happening at these different points marked on the phase diagram. My first point is this one, where I have the pure solid phase. So what is the value of P, the number of phases here? Then I say that P is equal to 1, and therefore what is F? F is equal to 2. So what does it mean? Here I would say that as long as I have P equal to 1, I have 2 degrees of freedom to describe this single phase of the substance. So in this case, what are the different 2 degrees of freedom? Temperature and pressure. So irrespective of what the value, I can just give the values of temperature and pressure. The corresponding point on the pressure temperature phase diagram is going to represent a single phase. In this case, it is a solid phase. Now when I come to the purple point as shown here, I am on the liquid and solid coexistence line, and therefore here I have P equal to 2 because 2 phases coexist in equilibrium, And therefore, I understand that F now is going to be 3 minus 2, that is equal to 1. Therefore, under the condition where I have two phases coexisting in equilibrium, I can vary only one parameter, which means that I cannot independently vary both temperature and pressure now if I want to have both the phases in equilibrium. It means that if I fix the temperature along this particular curve, there will be a corresponding value of pressure that will tell me that there will be a corresponding value of pressure along this line that will tell me that both the solid and the liquid are coexisting in equilibrium. And that is the reason why instead of a two-dimensional representation, I will have a one-dimensional line here representing the variation of equilibrium between two coexisting phases in the phase diagram. Now let us have a look at this point where once again I have a pure liquid phase, and therefore I don't have to have some kind of a dependence of pressure on temperature at which the liquid is at equilibrium, etc. It's a single phase. But the moment I come to this particular point where the liquid and the gas phase are in equilibrium, then I understand once again I have reached that part of the phase diagram where I have only 1 degree of freedom and I cannot vary temperature or pressure independent of each other. If I vary temperature, the pressure will have a fixed value at which the two phases, liquid and gas, will be at equilibrium. And this basically applies to the final points that I have shown here. But once again, I would ask you to look at this particular point. This is the triple point. At the triple point, by definition, how many phases coexist in equilibrium? 3. And therefore, for this pure substance now, the number of degrees of freedom is equal to 3 minus 3, which is equal to 0. Now, what does it mean? It means that here the temperature and the pressure values cannot be varied if you want to see all the three phases in equilibrium, and therefore a triple point is a characteristic constant for every pure substance. Now, with this background in mind, let us have a look at some typical phase diagrams that we come across in the experimental literature. So this is the phase diagram of carbon dioxide, and here you can very clearly see that you have the solid phase, liquid phase and the gas phase, and beyond the critical temperature what you have is a supercritical fluid where you can change the density of the fluid from liquid-like to gas-like values without encountering a gas-liquid meniscus in between. Now, very importantly, if you read out this phase diagram, what would be your conclusion on the melting point of solid carbon dioxide at higher pressure? At 1 atmospheric pressure, this is 1 atmospheric pressure. As you see that there is only equilibrium between the solid phase and the gas phase. Therefore, I would say that at normal atmospheric pressure, the only phase transition that carbon dioxide can undergo is the sublimation. On the other hand, if I am cooling sublimation on heating, if I am cooling down gaseous carbon dioxide, that means I am decreasing the temperature in this direction, then the gas will undergo deposition at 1 atmospheric pressure. And because there is no gas liquid coexistence line at normal atmospheric pressure, as I extend it to the higher temperature, I would say that at normal atmospheric pressure, carbon dioxide cannot be liquefied. Or I can otherwise also say that if I want to liquefy the gas, then I have to go at least beyond this point at a pressure higher than, say, 5.11 atmosphere, such that I hit the liquid gas coexistence line. And also I find that if this is the line for the melting of solid carbon dioxide or dry ice, now if I increase the pressure, so if I increase pressure, where does the equilibrium, where does the temperature go for the equilibrium between solid and the liquid phases of carbon dioxide? I find that the melting point increases as this line has a positive slope. But this is not actually a very generic observation. If you look at the phase diagram of water, which is a very complicated one, you will find that here also, once again, the solid and the liquid phase, it is separated by this phase coexistence line. And this and we find that on increasing on increasing pressure, the melting point of the liquid is going to decrease. So let us look a little more closely on the location and the shape of phase boundary when two phases alpha and beta of a pure substance coexist in equilibrium. So here is a typical phase diagram that one obtains from experiments, and the solid curve that is shown in black over here, this is the phase boundary between the phases alpha and beta of a pure substance. Now let us first look at the point A. At the point A, the phases alpha and beta are in equilibrium with each other. Therefore, I can say that at the point A, mu alpha Tp must be equal to mu beta Tp. Now, if I look at the other point B as marked on the phase coexistence line or the phase boundary, I understand that once again the system will have two phases, alpha and beta, in equilibrium with each other. But at this point, now I have a coexistence between the two phases alpha and beta in equilibrium at a temperature T plus dt, where dt is this amount, and P plus dP, where dP is this amount. Therefore, the condition of phase equilibrium at the point B would now read as, at this point the value of mu alpha must be equal to the value of mu beta. Now, as I understand that I can write down mu alpha at this point B as mu alpha at Tp plus d mu alpha. So what is d mu alpha? D mu alpha is the change in chemical potential of the component alpha as I changed the temperature of the system by an amount dt and the pressure by an amount dP. And this I can following the same logic, I can say that the new value of mu beta at this new point B can be written as mu beta at Tp, the value of mu of beta at the point A, plus d mu beta. Now, if it so happens that I understand at A the system was at equilibrium, then this condition is valid. So, combining this condition and this condition, I immediately conclude that along the phase boundary, d mu alpha must be equal to d mu beta. This also tells us that I can go back and think about the relationship of d mu with dt and dp. For the ith component present in the phase equilibrium, I know that d mu of the ith component, that is dependent on dt and dp. So for the ith component, this coefficient is negative of molar entropy for the ith component, and this coefficient is the molar volume of the ith component. So I am going to rewrite each d mu alpha and d mu beta and replace them with this expression on both sides of this equation. When I do that, this is the expression for d mu alpha and this is the expression for d mu beta. Now what I'm going to do is I'm going to collect the terms dt dependent on dt on one side of the equation and collect the terms dependent on dp on the other side of the equation, do a little bit of algebra, and this is what I get. I get that dp dt, that is equal to a difference in the molar entropies between the two phases alpha and beta divided by difference in the molar volumes of the two phases alpha and beta. And I can very easily now write down that dp dt is equal to delta S as beta goes to alpha divided by delta V as beta goes to alpha. Now, this basically tells me that if there is a change in the equilibrium pressure and temperature by amounts dt and dp, therefore dp dt would be related to the change in entropy of the transition and also on the change in volume of during the transition, and this equation is known as the Clapeyron equation, which quantifies the functional relationship between equilibrium pressure and temperature on the underlying thermodynamics of the system involving the change in transition entropy and change in transition volume. In the next lecture, we are going to discuss the generalization of Clapeyron equation to solid liquid, solid gas as well as liquid gas transitions and a coexistence of each pair of these phases for a pure substance, and try and understand as to why in some cases with increase in pressure the melting point decreases, in some other cases with increase in pressure the melting point increases, and so on and so forth. Thank you.